It's Paul. I'm going to do a proof for you of the equality of crossed partial derivatives, which underlies the well-known results that the curl of a gradient is 0 and the divergence of a curl is 0. I'm going to do this using a new tablet that I just received for my birthday. You'll have to bear with me because I'm just using this software for the first time. Let's start by drawing a diagram to illustrate what's going on. I'm going to draw some arrows. And let's put a couple of vectors in different colors along the two coordinate axes. There's one. There's the other, both supposed to be roughly the same length. And let's put a couple of lines on here. Here is a horizontal line through that one, and a vertical line through that one. Now let me label my points. Here is point A. Here is A plus t times the standard basis vector E sub I. Here is A plus t times standard basis vector E sub j. And here, of course, is A plus t E sub I plus t E sub j. Now let me explain to you how the proof is going to work. Here is an expression involving the function f evaluated at 4 different points, and it involves E sub I and E sub j in a precisely symmetrical manner. The value of f here goes in with the plus sign. The value of f down here at A also goes in with the plus sign. The value at A plus t E sub I goes in with the minus sign, as does the value A here. So you can think of moving down from this point toward the origin, and as you let t get smaller and smaller, you take the sum of the values at these 2 points and subtract off the sum of the values at those 2 points. That quantity goes to 0 really fast. In fact, it goes to 0 so fast that even when you divide it by t squared, the limit when t approaches 0 still exists. What I'm going to prove is that that limit can be expressed as the ith partial derivative of the jth partial derivative of f, but since this expression is completely symmetrical in I and j, I could have done it the other way around, and that will constitute a proof that these 2 second partial derivatives are equal when done in the same order. How am I going to do this proof? Well, let's draw another little arrow. Like that. And think about the difference between the function value at the head of the arrow and the function value at the tail. So we will have a plus sign here, a minus sign there, and that difference is the function g of s. Here is s. Look at it carefully. There's g of s. What are the first 2 terms here? And what are the second 2 terms? Well, the first 2 terms look an awful lot like g of s, don't they? It's just that instead of having s multiplying E sub I, I have t multiplying E sub I, and therefore I can rewrite that term as g of t. Second two terms, I've got a t e sub j here, but I've got nothing at all involving e sub I. S is equal to 0. This is g of 0. So this quantity we're interested in can also be expressed as g of t minus g of 0. Let's think briefly about g prime. What happens when we differentiate this first function with respect to s? Well, strictly speaking, we're applying the chain rule, and we have to calculate the derivative of f, but the only partial derivative that matters is the ith partial derivative. This is the ith partial derivative of f evaluated at a plus s e sub I plus t e sub j. When I view this as a function of s only the ith variable is changing. Second one is very similar, except that we don't have the t e sub j. The derivative of the second term with respect to s is just the ith partial derivative of f evaluated at s plus a plus s times e sub I. Now I'm going to apply the mean value theorem. The mean value theorem applied to this function of one variable says g of t minus g of 0. That's what we're interested in because it's the quantity that we're going to divide by t squared and take the limit of. And of course the mean value theorem just says that's equal to t times the derivative g prime evaluated somewhere in between 0 and t. And for the sake of simplicity, I'm going to assume that t is greater than 0, so I don't have to fuss around with absolute value signs. Now, we're assuming not only that f is differentiable at a, but that also each of its partial derivatives is differentiable at a. So I'm going to use that fact, since d sub I f, perfectly good function, is differentiable at a, we can use the definition of differentiable. We take the limit as t approaches 0 of 1 over the length of the increment. Let's figure out what that is. We're looking at the function d sub I of f evaluated at a plus c e sub I plus t e sub j. And so our increment involves a c and a t, and the length of that increment is 1 over c squared plus t squared. But c is something in between 0 and t. Since we're going to get something that is equal to 0, it really doesn't make any difference whether we divide by that or divide by t itself. Okay, differentiability. We've got the change in the value of the function. And if the function is differentiable, we can subtract off the derivative acting on the increment vector. That gives us minus c times the partial derivative with respect to the ith variable of our function d sub I of f evaluated at a. We also have to subtract off t times the partial derivative with respect to the jth variable of the same thing. Divide by the length of the increment, let t approach 0, and we get 0. We can do the same thing if we start out with just the function d sub I f evaluated at a plus c e sub I. In this case, I only have to subtract off one of these terms. I'll get 0. Strictly speaking, since my increment is c, I should divide by c. But since c is somewhere in between 0 and t, alternatively I can divide by t. Now I'm going to subtract those two results. When I subtract, I have the limit as t approaches 0 of 1 over t. Those two terms cancel out. Those two terms cancel out. So I have the ith partial derivative evaluated at a plus c e sub I plus t e sub j minus that same ith partial derivative evaluated at a plus c times e sub I. And I still have to subtract off t times the partial derivative with respect to the jth variable of d sub I f, again evaluated at a. Let's make that look a little bit clearer. And that gives me 0. Well, the second part's going to be easy. The t's just cancel out. What about the first part? Look at that. Can you see it anywhere else? Oh, yes, it's up here, isn't it? Only difference is we had an s up here, we've got a c down here. So this is equal to g prime evaluated at c. And now we are very nearly done. Because we know what g prime of c is. G prime of c is equal to g of t minus g of 0 divided by t. So the limit as 1 of 1 over t squared. Why 1 over t squared? Because I'm going to replace this g prime of c by g of t minus g of 0. But when I do that, I'm supposed to divide it by t. I put the t out there. Minus, well, since I put another t outside, I guess I better not put another t inside. And what have I shown? I've shown the limit as t approaches 0 of g of t minus g of 0 over t squared is equal to the partial derivative with respect to the jth variable of the partial derivative with respect to the ith variable evaluated at a. But what is this g of t minus g of 0? It's something that involves I and j in a purely symmetrical way, and therefore, if I interchange the roles of I and j, I've got exactly the same thing. And my result is proved. Nifty, huh?